Hello and welcome everyone. Let's continue where we stopped with trees. We discussed in the previous video that binary tree is one of the types of a tree and we'll be exploring it in detail in this video since a lot of algorithms ask most binary tree based questions. We already said that a binary tree is a tree where each node has at most two children. A node can have no children, one child or two children at most. This is different from the regular property of a tree that can have as many children as possible. We also said that the left child, the children of a node, are most times identified by the side on which they are placed, which is either the left side or the right side, and we call them the left child and the right child. We also discussed some properties, some terminologies of trees which applies to a binary tree too, which is a kind of tree. We discussed the terminologies, if you recall, the parents, the ancestors, the node, edges, depth, height. We discussed the properties, which is actually depth and height. We discussed the operations, and in this video we would be writing the code implementation. For the operations of a tree, we have to obviously create the node class. We said that a node structure would have its value, it would have the address to its left child and the address to its right child in memory. So be creating the node class, would be inserting a node into the node class, we would be searching for a node because we need to find a node in our tree, we'll be deleting a node, and we'll be traversing. But truth is that searching, deletion, even insertion, they are all traversals, right? Because traversals just basically means like looping, traveling through the tree. If you want to do anything at any point in the tree, you have to traverse from the roots. The way the node is structured, we have access to the roots, and from the roots we have to find a way to get to every other node. So traveling down from the roots to any other node is a traversal. So in case you want to insert, search or delete, we still have to traverse. So first to create a node, insertion, and then we'll touch on traversals. And you can recall from the last video we talked about the two major ways of traversal: the breadth first search, which is also called the level order traversal, and the depth first search. And under the depth first search, we also have three major ways of traversal. This is the preorder, where we traverse from the root of the tree, then we go to the left child and the right child. The inorder, where we traverse from the left child, the root, and then the right child. And the postorder, where we traverse from the left child, the right child, then to the root of the tree. And in this video, we'll be writing the code implementation and seeing how that translates to code. Let's jump right into it. Alright, so first off, let's create a node class. And recall that a node class is basically the casing for every node in our tree. Our tree is made up of several nodes. So we want to create a node class for each node in the tree, and let's write that. Saying it might be conceptualize it better. So we'd have a node, and each node I'm just defining class and function in Python. So I'm going to pass in data parameter. We don't need this default boiler code, and each node class is going to have a data value, is also going to have the address to the left pointer, which at this point is none, because on creating a node is not pointing to anything else. So I'm just going to manage that, okay, we are creating the root of a node first. It's not pointing to anything at that point. So the pointer to its left address, which we just call left, is none, and the pointer to its right address is going to be none. The JavaScript equivalent code is going to be somewhere on the screen. To just save time rather than coding that up, it's going to be somewhere on the screen, and I'll also link the code for the JavaScript and the Python in the description. So now this is the node class which we have created, and we can just test that this works by first, let me just create another function that can print the values in a tree. It's going to take itself as an object, and we're just going to print self the data. All right, so let's initialize a variable and create a new node. And how do you create a node? So basically we are calling the node class, we have the data passed into it, that's thing. And if we try to call root.print tree, This root.print tree basically is going to take this node class that we have and print out whatever data is in it. So if we print this, we can see that we have the value 10, which is indeed our node that we have created. If you don't want to print the data and we just want to see what this object looks like in memory, I can just go ahead and run this, and we can see this node objects stored this way in memory. I think JavaScript can explicitly show you the object class. Then you can see that the left is none, the right is none. We might have a look at that just to show you what I mean, but this is how it's going to be displayed in Python. So this is the JavaScript code. We are creating the same node class as we did in Python, and we've defined the object similarly to what we did with Python. We have written the constructor because we need it to in an object in JavaScript, and we are getting the data at the left and the right, which is initially set to null, and the data is going to be whatever we set it to be, just the same thing we did with the Python but different syntaxes. What I want to show you is actually what it is stored like, what the node is stored like in memory, and JavaScript is going to show us that better than Python. So you can see that we have a node class. Its data is 10, its left is null, and the right is null. So occasionally when I want you to really visualize this, I would switch to the Python code to just show you how this would log to the console, because so far I've seen that Python just shows the addresses and we can only get the data, but this might help us visualize that, okay, this is a data, right? Its left value is currently null and its right value is null. When we start adding left or right children, you can then see that, okay, its left child is already pointing to this node and its right child is pointing to the other node. So we can just test out inserting some values to the node tree. For instance, we have the root of this tree, so I can insert at the right side, I can insert a node of 23. At the left child, I can insert a node of 5. This should be left. Then on the right child of the left child, I can insert a node of 15. And to visualize, this might look something like this. So at the node would have 10, right? And the right child, on the right child, we would have 23, right? That's from line 20. We'll have 23. On the left child, line 21, we have node 5. Just going to give us some room. All right, we have 5 on the, let's try to, okay, so on the right of the left child, so this is the left child, right? 5 is the left child, and on its right child, which is going to be this, we're just going to have a 15. So visually, this is what our tree would look like. Now, if I was to run this code, if I was to npm run py, because we're using print tree, okay, we're printing the self, that's self.data. So I'm just going to give ourselves, just print the data, not the node address, and we can see that we're printing the root. But if we print the root, let's print the right child. So root.right.print, this should give us 23 because we are printing the right child, and this is 23. And if we should print the root.left.right, no, this is, okay, root.right.left, so this is the right child, and so that diagram wasn't accurate. The left of the right child is 15, not the right of the left child. All right, so the right child, which is this, then the left child of the right child would have a value of 15. So now let's print that, and we're going to write the insert code, right? So this is just a basic rundown of what this looks like. This is 15, but if we do something like the right child of the right child, we should have a none because there is no right child on this right child. So if we print this, this is going to give us a non-type. So non-type has no attributes print tree. The value is none. So I'm going to log what this code looks like in JavaScript so we can see all of the relationships between the. So this is our JavaScript code, and similar to what we have with Python, we have the node, we are attaching the right child, the left child, and the left of the right child. And if you notice, we can't just append a value, say 10, 23, 5, or 15 to the node, to the tree. We have to first wrap it in the node structure object, and this is because it has to have a left pointer and the right pointer to qualify as a node to be in a tree. So first have to insert our value into its node structure. So let's log this and see what the structure looks like now. Perfect, this is what we want. So we have a node. The first data, which is the root, is 10. The left child has a node of 5, and the image that we drew for our Python will be on the screen somewhere, so you can see how that is drawn. So the node on the left child is 5, and the right child has a node of 3, and then the left child of the right child has a node of 15. So we have the data, we have the left, we have the right. Then the right child as a data or a value of 23, and the left child of that right child is 15, like we saw with Python, and the right child is null. If we choose to log root.right.right, this should give us a null, because like we can see from here, root.right is null. We have no value there, and as we can see, that is null. But if we choose to log root.right.left, this is going to give us the value of 15, the node. And if we just log the data, this is giving us the node directly, but if we log only the data, we can see that we have 15. All right, cool. So let's go back to our Python code. Now we are switching in between languages, and I hope it's not in any bit confusing. It's the same structure and the same logic, just different syntaxes. All right, so this is a good way of linking the values or connecting values in a tree, but it's not the most appropriate because, for instance, it is not maintainable. Our tree can go as deep or as high as we want it to, and we would get confused at some point trying to find the root.right.left. Then if we had something like root.right.left.right.left and trying to append all of these nodes, it just doesn't make sense. It's just easier to write a function for it. And the function we are going to write is going to follow the properties of a binary search tree. Now, if you recall in the videos on trees, we discussed a special kind of tree, binary search tree, which is a kind of binary tree itself. It has the same property as every tree can only have 2 children at most, but the property that differentiates it from binary tree is that its left child, the left child of a root, the left child of a node must be less than the root, and the right child must be greater than the root. For a binary tree, we can have 50 here and then we can have 2 here, but this doesn't work for a binary search tree. A binary search tree must follow the property whereby the left child must be less than the root and the right child must be greater than the root. And for every subtree, for instance, this is a subtree, it has its own children. The left child would also follow the property that it must be less than its root, and the right child must be greater. Let's say we have 87 here, for instance. We have 15 here, and then we have 87 here. So even the children must have this property. The subtrees must have the property of a binary search tree. Now we're to write a function. Why I'll be choosing to write this function of insertion is because it just clears out that decision. For instance, if we wanted to insert, right, this is the algorithm for inserting. Let's say insert, right, we have a value that we want to insert. What is the algorithm going to look like? Is there a node? Do we have a node? If we don't have a node, then no, make the new value the root, not node rather, make the new value the root. Let's assume that we don't have all of this. If we do not have all of this and we want to insert a new value into our tree, then if there is no root, there's the logical next step to take is to make that first value our root. But what if we already add a root? If we already add a root, then we now have to decide, do we put it as the left child or as the right child? Now, how do we know when to put it as the left child or the right child? We can put it as the left child if the left child is already complete, right? For instance, if the left child has both left and right child, then we can just say, okay, you know what, the left child is a complete tree, is a full subtree. Let us move over to the right child, right? Now, is the right child complete or not? But this is a little bit more complex than it needs to be, and it's not necessarily complex writing code, but it's a bit unnecessary. We can just use the binary search property to make this decision for us. How do we decide whether to put it on the left child or on the right child? Is the value less than the node? Yes, then we put it on the left child. Is the value greater than the root? I don't know why I keep writing node because they are all nodes, right? If the value is greater, less than the root, we add it to the left child. If the value is greater than the root, then we put it on the right child. And basically that is just the algorithm for inserting into a binary tree. But this particular property, like I said, is peculiar to binary search tree. Ideally or conventionally, a binary tree doesn't care if its left child is greater or its right child is left. A binary tree just says that, you know what, I can only have 2 children and that's it for me. But when we want to write the function for inserting to cut down the decision fatigue of, okay, how do I arrange this? How do I check if the left side is full, if the right side is full? We can just steal or borrow rather the binary search property of putting the lesser value on the left child and putting the greater value on the right child. It started to rain, so if you hear any sound, I apologize. Alright, so let's write the code for the algorithm we've already written. So first we want to check if there is a root, and if there is no root, we just make the new value the root, right? So we can just check that, okay, is there a root? And recall that we called our root self.data, but I think to make it clearer, let's just call it the root actually. So we can say that, you know, if self.root exists, if it exists, then we want to basically check if it's less than or greater than, else we just want to make that the new root. So just make it node and the data. So basically we are calling the node of the data, right? So then we want to check that, okay, if the root exists, and we can just go if the data is less than the root, right? If the data that we currently have is less than the roots, the data in the roots, then we want to go ahead and add that to the left child, right? But to be sure that, because it is possible that our left child is also filled up. For instance, if we have 2 here, let's imagine I already have a tree that is like this. I want to insert a number like 14, or let's just choose a lesser number than 10, which is going to be 7, right? So we have our roots, we have our left child, but 7 is definitely less than the root, so we know that we want to insert it on the left child. But we cannot just go ahead and insert it on the left child because there is already a left child. So we have to now look down that tree and see if there's anywhere we can put it, right? So first, after we see that, okay, our value is less than the root, so we know we have to traverse down the left side. But we now have to check, is our left child even empty at all? If self dot left is less, is none rather, if it's empty, then we want to go ahead and just append that child to our left child. But if it happens that it is not empty, then what we want to do is that we want to traverse down that left tree, because we know that, look, you are going to be on this left side. That is where we want you to be, because you are less than our root, given the property we are following, that the left child must be less than the root, right? Stick with that property. So now we're not checking that, you know what, 7 has to be on the left side, but the direct child to the root is not empty. So we want to go down the left child and see if there is any way we can fix this value. We want to traverse down that subtree. So what are we going to do? We're just going to call the function on the left child of this subtree, and we are going to pass in the data. You know, we'll just continue to traverse the left side of this tree till you find a place that you can put this node. I know that eventually left is going to be none, and we're just going to find a place to put it. But if our data, what if we're not giving 7 but we're giving 17, right? And we want to insert 17 into the root. So we check, is 17 less than the root? No, 17 is not less than the root. So what do we do now? We look at the right side. So we check if 17 is greater than the root, then like what we did previously, we want to check if the right child is empty. If it is, then we just want to go ahead and append the child to the roots directly. But as we can see, we are following the premise that this is what our tree currently looks like. So this is not empty, right? So what do? We just traverse down that right tree, the right subtree, and we just insert. We call the function on the right subtree. This is recursive, and we just follow this premise, right? So let's test out our code and see how it works. So the first thing that you notice is that we do not need to start creating nodes. We do not need to start defining where we want to place our node on creating our value. We don't need to create every node every single time. What we need to do is create our root node, and then we don't have to start deciding, okay, do I want it on the right left, or do I want it on the left child? Our code is going to, our function, the insert function, is going to undo this for us. And so what are we going to do? We're just going to call this function roots.insert. We already have an insert here, and what does it need us to pass? It needs a data. So let us pass 2, right? Given that our node, we've defined our root node as 10. Let's still follow this diagram basically. So we are inserting 2, and let's go ahead and insert what we previously had, which was 20. Let's go ahead and insert 15. Let's go ahead and insert 87, and let's also add our newcomers, which is 7 and 17. So basically our tree structure is going to look like 15, 87. Then we're going to have 7 on this side, but it's going to be on the right child of our left child, since it is less than 10, but on this subtree it is greater than 20. All right, cool. Greater than 2 rather. Cool. So let's also see what this is going to translate like. And 17 is greater than 10, is greater than 20. It is less than 20, is greater than 10, less than 20. So it's going to be on this path, this left part of the right tree, and is also greater than 15. So it's going to be on the right child of 17. So we're going to have 17 here. So this is what our tree structure is supposed to look like, and we can just test this. Okay, we already have roots. This is our roots dot right dot print tree. So roots dot right dot print tree is going to give us 87. So let's just what are we currently running? Node object has no attribute data. So we can just look at this and wonder where this is coming from. We can see that the error is going from line 53, okay, which is printing it, and line 33, which are printing self.data, and it's saying that the node object has no attributes data. Yes, so we've changed our attribute to root. this no longer has data. So let's rename this, run our command. Let's clear this out, and try to give this another spin. Just going to run npm run pi, and we can see that we have 87 because this is the right print true child. And then we go from, okay, this is right, left, and right. So right, left, and right. This should give us a new comma, which is 7. And if we try to run this, okay, right, root right. No, I meant to type root left dot right. So this is root, not 17. But yeah, we did get a new comma. If we go back to that, we say that root dot right. This is root dot right. Then left, the left of this right is 15, and the right of that left is 17. That is accurate. So now let's go back to root left then right. So that's going to be root dot left dot right. If we print the tree, we should get 7 this time around. All right, so let's look at the relationship, what it looks like in our JavaScript code. All right, so this is our code for JavaScript, and one of the first things you see is that we created a different class constructor for the binary tree. We have a different class for that is encasing our node, and we are defining our root to be set as null initially, because when we have a new tree, obviously we have nothing. And then we're trying to insert, and our insert function takes 2 parameters, takes 2 arguments, the root and the data. So the root is going to be initially set to null, but we really don't care. Whatever the root is at that point, we're going to run with it. And then we're creating our new node from the data given. Recall that we are giving the data in number, integer is number, string, or whatever, and then we want to convert it to a node constructor. And so that is what line 18, this line, is doing here. And then when we've created that node from the data given, we want to check if our root is null. If our root is null, then it just makes sense that the first item that we insert into the tree is the root itself. But if our root is not null, we want to check if the data is less than the root dot data. Recall that the way JavaScript is, we don't have access to the data directly like self.data with Python. With JavaScript, we have the root, which contains all of the information about that root, its data, its left address, and its right address. So we have to do this dot root dot data to access the data of the root. So if our data is less than the root dot data, similar to what we had with Python code, then we want to check down that part. So first we want to check if the left is null. If it is, we can just go ahead and insert our node in the left child. But if it isn't, we want to traverse the left child and the data given. Basically, we are calling the function on itself, this dot insert. Now we are traversing the left child of the root, then we're inserting the data. If the data is greater than the root, then we want to traverse down the root child, similar to what we solved with the Python. And then we're just going to go ahead and run this code. I don't remember the scripts that I had called the JavaScript. Okay, start JS3. So we're just going to go ahead and run this. And okay, we have only 17. This isn't accurate. We should not have just 17. We should have the full tree. So now we want to check why we have just 17 and not the full tree. Try to debug this. I really can't figure out what is going on, as it has worked previously, but then I removed the extra data set that I added and tried to run it again, and it gave me the structure I was looking for. But if I add one more data, I can see that it completely ignores the other one. I'm not sure what this phenomenon is. I think that it probably can't log as much, but yeah, this is weird. If you have any reasons why it's behaving this way, I would appreciate it in the comment section, and I'll also continue to debug, But yeah, this is a weird phenomenon for me. All right, but let's try to work with the data set that has been logged to the console. So you can see that we do not need to start telling our code, this store 2 on the right side, or store 20, store 2 on the left child, or store 20 on the right child. Because we have written our code on autopilot, it knows that, okay, there is no root node, right? So 10 is the root node, 2 is less than 10, so it's storing 2 on the left child, and the 20 is greater than 10, so it's storing 20 on the right child. Normally, I think what we had previously, it was able to nest these values, right? And if this had worked as I thought it would, then 15 would have been stored as the left child of this right child. All right, so if I'm able to figure this out, I am going to make a back I'm going to walk back to it and just show you how it's done. But I'm hoping that you get the idea and we can just move on with this. So far, you can see that we've only been able to print a data per time. So as you can see, we are either let's run our code again. We are either getting a node or the value at a particular node, the left of the right child, or the right child, or the right of the left child. Basically, we are visually looking at our tree and just picking out a data to log. And if we do not pick out any data, it's just going to log the data at our root, which is 10. But what if we wanted to have access to all of the data? What if I wanted to look at all of the data in the tree at a given point? So we can just check. This is our print function, and we can just check if self.left, if we have self.left, if there is any value in the left child of our tree, then we want to traverse down this path of the tree, the left child of the tree. Likewise, if there is a right child of the tree, we also want to traverse the right child of the tree, and we're also going to be printing the self.roots. Eventually, when we traverse the tree, we are going to get to a place where there is nothing else to traverse, and so what we've previously called is going to start popping off the stack. Basically, we're doing this recursively. We're printing the roots, and then we're traversing the left and the right child and printing all the values. Now if we go ahead and run this, you can see that we have 10 to 7, 20, 15, 17, and 87. We are printing the roots first, and the root is 10. Then we're printing the left. You see, we are printing the left child, and that is 2, and then 7. Then we're printing the right child. That's 20, 20, 15, 17, and 87. Let's try to conceptualize it better, because this method of traversal is a depth first search, and since we are using the recursion uses the call stack. Recursion by default uses the call stack, which is already built inside the memory capacity. So a recursive function uses the call stack already. And now we are using the call stack to traverse this tree and get the values in an order called the preorder traversal. The preorder traversal, if you remember the rule, it is the root. We're traversing the roots, then we traverse the left child of the tree, then we traverse the right child of the tree. We are giving the values 10 to 7, 20, 15, 87, and 17, and we inserted them in our binary tree, right? So they sort of look like this. And we discussed that one of the ways that we can have access to the nodes, the individual values in this tree, is through the preorder traversal, which we just did now, in which we traverse the roots, the left child, then the right children, and we kind of like got the values from there. But how does that really work when we talk about preorder traversal? So the first thing we do is we look at the roots, right? Because preorder is literally roots, left child, and then right child. This is how the traversal works. So we look at our root node, which we're giving 10, right? And then we look at the left child of that node, which is 2. Then if we add the left child of 2, we would look at that left child because we are going towards the left path before coming back to the right child, but we don't have a left child. That's the end. So we go to the right child of that left tree. Recall, we are going to traverse the left subtree before moving over to the right subtree. So our left subtree, we are traversing even the left subtree of our left subtree. And when we get to this point where there are no left subtrees of our left subtree, then we traverse the right subtree of our left subtree. Preorder just basically means we have roots, left we traverse the left children first, and then we traverse the right children. Then we go over to our right subtree and we get the value 20. Then we traverse that left child. The left child leads to 15. Then we get 17. Then we finally get 87. This is what the preorder traversal looks like. Now we've looked at the code of this Preorder Traversal, but this is just an illustration in case it wasn't too clear. We kind of just jumped right into the code without looking at how this works. And then we have the Inorder Traversal. And the Inorder Traversal, I think I said the cookie is in the name or something. That made no sense, but I wanted to say it again, that the Inorder Traversal basically just means the root is the main thing that we're using to differentiate all of these traversals, and left is always going to come before right. For preorder, we have roots coming first, then left and right. Then for Inorder, we have root is in the middle, then left and right on either sides of it. And then lastly, we have the Postorder Traversal. With posts, root is going to come last, then left, right in that order is going to come before it. So now we've looked at the preorder. Let's look at the Inorder Traversal. So for our preorder, we have the left, the root, and then the right subtree. So we're going to go down to our left subtree first. So this is our left subtree, and then if there was any other thing down this path, we'll traverse. So this is the least subtree in this left subtree, and for each subtree we have to follow the same Inorder Traversal. So this is our last subtree. This is the only subtree we have for the left subtree. When we look at this and we try to do left root right, there is null value in our left, so we ignore that. We go to the root of our left subtree, which is going to give us 2. Then we consider the right child, which is going to give us 7. Then we now consider the larger subtree, and its root is 10. Then we move over to the right subtree. We look at this subtree and we kind of say that, okay, this is a subtree which also has a subtree here. So we consider this subtree first. We look at its left child. It had no left child, so we ignore that. Then we consider the root. Then the root is going to give us 15. Then we consider its right child, which is 17. Because for each subtree, we also have to follow the Inorder Traversal. Then after settling the subtree of the subtrees, then we look at the larger scope to which this 15 belongs to. Recall that this 15, the value 15, is just a subtree of this subtree, and that is why we need to run this recursively, otherwise we'll be repeating a deep amount of code. We're running the same code on each subtree till we get to a base case whereby, this is the last subtree in this case. So basically this is what we are doing, and this is why the recursive code works just fine. Now that we have considered this subtree, then we've traversed its values and found out that it is a subtree. It is a part of this larger subtree. So if we traverse the subtree, the next value to be printed is 20, and then we can go over to 87. If 87 had a subtree, would have traversed the entire subtrees of 87, and this is going to be our values for our this is going to be the values that we get for Inorder Traversal. So let's look at the code quickly. So previously we are printing our roots. This is what we had for our preorder, where we are traversing the root of the tree before traversing the left and the right child. Inorder just means that, okay, we are traversing the left child of the tree, then want to traverse the roots, then finally we are traversing the right subtree. And we're basically just printing out the values here, but you can do anything with it, solve algorithms with it, store the values in an array, anything you really want to do with it. But this is just the format you would follow, where you are traversing the left subtree, then traverse the root, and finally the right subtree. So if we try to run this, we should get the same values as we did during our code walkthrough, where we got 2 first because 2 does not have a left child, so we then move to the root. The left was null, so we could safely ignore the left child. No need to print out null. We print out the root, then we print out the right child, left child, root, right child, left child, root, right child. That is in order. The root is in, then left subtree is prior, right subtree is prior. And I noticed that I've been saying left subtree, left child. I hope it's not confusing. I'm using them interchangeably. They basically mean the same thing. Now that the left child has been traversed, then we can safely get out the root and then move on to traversing the right subtree. And even in the right subtree, we could see that we still have a subtree, and then we traverse that subtree 15, 7, and its non-existent left child. Then we log 20, and finally we log 87. Finally, on depth first search traversals, let's consider our post-order traversal, which we said that it is basically the roots being traversed last. So we'd have the left child or the left subtree, we'd have the right subtree, and then we'd have the roots for every subtree, similar to what we had with the Inorder and Preorder Traversal. So we can look at the leftmost subtree, right? Left subtree, left child would always come first. And we look at its left child, there is none, because we are going, let me just have this up here, left, right, root. We look at the left child, there is nothing. Then we look at the right, so we have 7. We look at the root, we have 2. There is nothing else for us to traverse on this subtree, on the left subtree. So we go to the right subtree. In the right subtree, we can see that similarly we have another subtree, so that has to be considered before the larger subtree. So we're going to be digging deeper, depth. We're going down the tree, the depth first. So then we are traversing the left, right, and root of this subtree. When we traverse the left, there is nothing on the left, so we traverse the right, we have 17, and we traverse the roots, we have 15. Then we look at our node, which is a bigger part. We look at the family of which 15 is a part of, and then we begin to consider traversing that part. So 15 had already been visited, so we consider its right sibling, and there is nothing to traverse down, so we just return 87, and then we return 20. And since we've returned the root of this, we've traversed the left and the right, so we can move on to our larger subtree and just return our root, which is 10. Translating this to code is going to be relatively easy, similar to what we've looked like. Pre-order, the root came first. In order, it came in between the left and the right, and post order is just going to come after we have traversed the left and the right subtree. And when we run this code, we should have 7 to 17, 15, 87, 20, and then 10. Traversing the left subtree, the right subtree, and then the root. Since we're on traversals, let us have a look at the breadth first search traversal, which is also called the level order traversal. And how this works is that we traverse our tree by the level. So the first level we're traversing is obviously the root node. We have 10, and then we move over to the next level. So we're going to have 10, we're going to have 2 and 20. Then we're going to move over to the third level, or the second level, since it's 0 index based. So the second level, then we're going to have 7, not 17. We're going to have 7, 15, and 87. And the last depth, or the last level, we're then going to have 17. So basically this is what the level order looks like. We are not going one direction deep in like we did with the pre, in, and post orders, where we are going, go left first, go right first. We are not doing that. In this case, we are going level by level. And if you recall what a level is from our trees video, levels is basically the points from which edges are coming into them. No edge is coming into the root, so it's at the level of 0 and you go down that path. You can just watch the previous video if you care to know what these terminologies are. But basically, this is what a level order traversal looks like. Now let's translate that into the code. All right, so I'm just going to go ahead and define this as breadth first search. I'm also going to pass an argument that's going to be the root, and then I'm going to use the queue data structure and store the roots in it. So basically, how a breadth first search works is a breadth first search uses the queue data structure first in, first out. Depth first search uses the stack data structure, but that is not explicitly defined in the code because we have we're using the recursive function which uses stack under the hood, so we don't need to explicitly define it because using recursion already uses it. If we had written it iteratively without the recursion, we would have to use stack, but we can just take advantage of recursion and its stack. So while our queue is non-empty, we want to go ahead and pop off the first value in our queue data structure because queue is first in, first out, and pop without the 0 argument is going to pop off the last element in our queue, but this is not in an array. This is why it's in an array to define our queue. So we want to manipulate our data to act like a queue, and we do this by adding this extra argument. I know what, don't pop the last item, pop the first item. All right, so just go ahead, and print the value in, I think this is node.data. Go ahead and print the value in our node. And if our node has a left child, we want to go ahead and append that to our queue. If it has a right child, we also want to go ahead and do the same. All right, so let's try to run this. And we have, okay, 7 to 7. No, we should have 10 to 20 since we are going level by level. And okay, we are still using our print tree. Let's just go ahead and call our BFS and pass in the root. When we run this, node object has no attribute on line 44. Let's look at what's going on. Okay, I don't think we're using data anymore. We are using root. Keep running into the same problem. So we're using root, and if we try to run this again, it should be fine. So we're getting our value 10 to 20, 7, 15, 87, and finally 17. We are getting it in a level order, which is what we want for breadth first search. And JavaScript developers, no, I did not forget you. The JavaScript equivalent code is always going to be by the side of the Python code. Yeah, so thank you for watching. I think I'm going to stop this right here so it doesn't get too long. In the next video on binary trees, I thought I'll be able to do all this in one breath, but turns out that I can't. We'd cover some part like searching, deleting, finding, and just some basic operations, other operations. We've looked at the insertion, we've looked at all of the traversals available. Now we'll look at other traversals, not other traversals, but other operations that we can also perform on trees, like searching, removing, and all of that good stuff. By the way, this is binary tree, but as you can see, the principles and the operations and the code applies to binary search trees. Thank you so much for watching. I'll see you in the next video.